So in this example, we are again looking at another important concept needed to verify the logically equivalent statements of the invertible matrix theorem. So again, we're not going to be seeing this invertible matrix theorem until section 2.3, but we're already beginning to establish the necessary connections needed to verify these logically equivalent statements. So here we go. We want to suppose that matrix A times matrix D equals the M by N identity matrix, where both A and D are size-appropriate matrices. Now, in this question, we are asked to show that for every and all vector B's in Rm, that the non-homogeneous equation, matrix A times vector X equals vector B, has a solution. We'll then want to go ahead and use this to explain why matrix A cannot have more rows than columns. So here we go. We want to start with our proposition or our hypothesis. Let's suppose that matrix A times matrix D is equal to that M by M identity matrix. So again, I sub M is the M by M identity. And we want to, of course, assume that matrix A and matrix D are size appropriate, or of a size such that the following holds true. So let's go ahead now and consider any vector B in Rm. Now, what exactly is our goal here? What is it that we want to show? Well, we know that we want to show that for every vector B in Rm, that the non-homogeneous equation has a solution. So we need to find a vector X that satisfies the non-homogeneous equation, matrix A times vector X equals vector B, for every vector B in Rm. So in order to do that, we'll start with our hypothesis, and let's right-hand multiply this by the arbitrary vector B in Rm. So our hypothesis, or our proposition, being that the product matrix A times matrix D is equivalent to the M by M identity matrix. And so we're going to take this and right-hand multiply by vector B. So what can we see occurring here? Well, we know that a vector times the identity matrix is certainly equal to that vector. So we'll leave the right-hand or the left-hand side as it is for now. And now, using the properties of matrix vector multiplication, we can reorder the terms on the left-hand side. We can say that this is the same thing as matrix A multiplied by matrix D times vector B equals vector B. And would you look at that? That's a non-homogeneous equation. So we can say that the vector X defined as matrix D times vector B satisfies the equation, or satisfies the non-homogeneous equation, matrix A times vector X equals vector B. Woohoo! That's exactly what we needed. And so we can say that, therefore, the equation, that non-homogeneous equation, matrix A times vector X equals vector B, has a solution for every vector B in Rm. And so we have verified the first part of this question. And we now want to go ahead and use this to help us explain why matrix A cannot have more rows than columns. So quickly, we'll think about what we just verified. So we have showed that the non-homogeneous equation matrix A times vector X equals vector B has a solution for every vector B in Rm. Now, we know that this statement is logically equivalent to saying that matrix A has a pivot position in each row. And this is by the equivalence theorem that we saw back in section 1.4. Now, since each one of these pivots is in a different column, this lets us know that matrix A must have at least as many columns as rows. Or in other words, matrix A cannot have more rows than columns. So since matrix A has a pivot position in each row, and since each pivot is in a different column, we're able to conclude that matrix A must have at least as many columns as rows, explaining why matrix A in this case cannot have more rows than columns.